In this video here, we're going to take a look at the scalar triple product. Now we can find the scalar triple product of three vectors, a, b, and c, and we can use this to find the volume of a parallelepiped and a tetrahedron. So to get us started here, then let's just say that we have these three given vectors. So I've got the vector a, the vector b, and the vector c here. Okay, and they're all given as follows. So if we cross the vector b and the vector c together here, we obtain this result. And this shouldn't be new to you, right? We did introduce this in the previous video. Okay, so b cross we see here gives us this result. Now, if we take this remaining vector a here, what happens then if we take the vector a and we dot that with this cross product here? Okay, so we have a dotted with this cross product here. Well, if we do that then, what we obtain here is the following. So a dotted with this cross product here, so b cross with c, gives us the following. And this result here then, so a dotted with this cross product here of b cross with c, this is what's known as the scalar triple product. Okay? So a better way to write this then is as follows. So we can also write this as the following. So a dotted with this cross product here then, so b cross with c, is equal to this 3×3 determinant here. So along the top row, we have a1, a2, a3. Along the middle row, we have b1, b2, b3. And then finally here along the bottom row, we have c1, c2, and c3. So obviously, if we just expand along the top row here, we just obtain this result here, right? It's just the same thing, but writing it in this form here is a little bit more intuitive, okay? So as we've already mentioned then, a dotted with this cross product here is what is known as the scalar triple product, okay? And again, as we've already mentioned here, it is quite useful to find the volume of a parallelepiped and a tetrahedron, okay? So before we look at some practice questions then, there is a couple of useful properties here for the scalar triple product. So as we just mentioned then on the previous page here, there are two important properties that you should be aware of for the scalar triple product. So for the first property here, then we say that the scalar triple product is cyclic. So what we mean by that then is a dotted with this cross product here is equal to b dotted with this cross product here, and that's also equal to c dotted with this cross product here, okay? And that's for three vectors here, a, b, and c. Now for the final property here then, so property 2, we say that if a vector product is repeated, then the scalar triple product is equal to 0. So in that case then, as you can see here, a dotted with this cross product is equal to a dotted with this cross product here. So as you can see then, we're repeating this vector product here. In that case, that would be equal to 0. And that's for any vector p here, okay? So that gives us our two properties then for the scalar triple product. So finally, before we look at some practice questions here, we did also mention on the previous page how we can use the scalar triple product to find the volume of a parallelepiped and also a tetrahedron. So let's just quickly look then at how we can find the volume of those by using the scalar triple product. So let's have a look then at how we find the volume of a parallelepiped, or sometimes this might be pronounced parallelepiped. Either way, it's just the same shape, but some people pronounce it slightly differently. So just so you're aware here. So if three sides of a parallelepiped are given by the vectors a, b, and c as shown in this diagram here, so just in case you've never seen a parallelepiped before, this is what it looks like, right? Then the volume of the parallelepiped is given as follows. So the volume V here is equal to the magnitude of the scalar triple product. So as you can see then, in terms of this result, nice and straightforward. But this is a result that isn't given in the formula book, so it is a result that you will have to commit to memorizing, okay? But in terms of the volume of a parallelepiped here, that's all we need. So let's have a look now at how we find the volume of a tetrahedron. So let's have a look then at how we find the volume of a tetrahedron. So if three sides of a tetrahedron are given by the vectors a, b, and c as shown in this diagram here, then the volume of the tetrahedron is given as follows. So as we can see then, the volume V here is equal to 1/6 times by the magnitude of the scalar triple product. And you might recognize straight away that this result here is very, very similar to the volume of a parallelepiped, right? The only difference now is we times through by 1/6. But other than that, very, very similar. And hopefully that might help you remember this result because, again, just as we saw with the volume of a parallelepiped, this result is also not given in the formula book. So it's one of those things that we do have to commit to memorizing. So in terms of the volume of a tetrahedron here, that actually gives us everything that we need here for this video. And that concludes this introduction to the scalar triple product. So all we're going to do now is work through a couple of practice questions here for the scalar triple products. So let's just get started then with question 1 here. So for question 1, we have this diagram of a parallelepiped. We're also given some vertices here. So we have A, B, D, and E. And the question then asks us to find the volume of the parallelepiped. So to begin with here, what I actually need is a few different vectors. We need this vector here. That's the vector AB. Let me just make a note of that as well underneath. I want the vector AB here. We want this vector here. That's the vector AD. Like so. And we also want this vector here, AE. Okay. And again, let's just make a note here to the vector AE. Because with these three vectors here, we can easily find the volume of the parallelepiped. So let's just start then by finding these three vectors here. So for the vector AB then, this would simply be B minus A. Okay. So what do we get here then? Well, we get -1, -1, so that's -2. We then get 0, -0, so that's just 0. And then finally we get 3, -1, so just be careful with the signs here. So I get 4 there. Okay. So that's the vector AB. Let's keep going here. So for the vector AD, this is given as, so it would be D minus A. So we get 0, -1. So we get -1 to begin with. We then get 2 -0, so that's just 2. And then finally 2 -1. Again, just be careful with the signs here. We get 3 there. Like so. And then finally here, we have the vector AE. Like so. So for the vector AE here, this is simply E minus A. So we get 2 -1, giving us 1. We get 1 -0, again giving us 1. And then finally, 2 -1, that gives us 3. Okay, so we have the 3 vectors that we need here. So we now have everything that we need to find the volume of this parallelepiped. Okay, so for the volume then of a parallelepiped, this is given as V is equal to the magnitude or the modulus. Don't forget you can just use those interchangeably here. So the magnitude then of the vector AE dotted with the following cross product. So we have the vector AB cross with the vector AD. Okay, like so. Now this here then is just the scalar triple product. And don't forget we can easily evaluate the scalar triple product by evaluating a 3x3 determinant. So in this case here then, this would be the following 3x3 determinant. So we get 1, 1, 3. We then get -2, 0, and 4. And then finally along the bottom row here, we get -1, 2, and 3. Okay. So at this point here, you could just use your calculator and evaluate this 3x3 determinant. And what that would just give you then is the volume. That would be the volume of this parallelepiped. If your calculator can't find this 3x3 determinant here, then unfortunately you just have to do it by hand. But by this point, right, we are doing further pure 1. Finding a 3x3 determinant should be pretty straightforward. So let's just go through that here. So what I'm going to get here then is 1 times by the remaining 2x2 determinant. I get 1 times by. So I get left with, well, basically just cross this row, this column. So I get 0, 4, 2, 3. So 0, 4, 2, 3, like so. We then get -1. So -1 times by, so across this row, this column. So I get -2, 4, -1, 3. -1 and 3 there. And then finally we get plus 3 lots. So 3 times by. the remaining 2 by 2 determinants. So across this row, this column, we get -2, 0, -1, and 2. So -2, 0, -1, and 2 there. Okay. So let's just evaluate this here as we go. So this 2 by 2 determinant here, that's going to be 0 times by 3 minus 2 times by 4. So I get -8 there. Like so. What do we get here then? So -2 times by 3, that's -6 minus -1 times by 4. That would be -2 there, but we times it by -1. I get +2 there. Like so. And what else do we have here? So -2 times by 2, that's -4. Times that by 3, we get -12 there. Okay. So -8, -12, -20, +2, we get -18 there. But don't forget, we take the modulus here of this value. Okay, so therefore the volume of this parallelepiped is equal to the modulus of -18, which is equal to 18 there. Okay, and there we have it. So that gives us the solution there to question 1. So moving on to the very last question here, then question 2, where as we can see, we have a tetrahedron with the following vertices. The question then asks us to find the volume of the tetrahedron. So as we can see for this question here, right, we don't have a diagram. So the first thing that we're going to do here is just quickly draw our own diagram. I've got A here, we have B, we have C, and then finally D here. Okay, so that's A, this is B, this is C, and this here is D. Okay, so if I join these up then, we'll get something like this. This will form our tetrahedron. Okay. As you can see, my art skills are certainly not the best, but don't really matter too much. You get the idea. Like so. Okay. This here then is our tetrahedron. Now what I need here, again, just like we saw for the previous question, is a few different vectors. So we want this vector here. That's this vector AB. We want the vector AB. We want this vector here. This is the vector AD. That's the vector AD. And we also want this vector here then through the middle. Okay, and that's the vector AC there. Okay. And with these 3 vectors here, we can then easily find the volume of the tetrahedron. So going back to my original pen color here then. So for the vector AB, this is given as B minus A. So we get 0 minus 1. That's +1 there. We get 4 minus 1, so that's 3. And then finally we get 4 minus 3, giving us 1. That's the vector AB. Now for the vector AC, this is giving us C minus A. So we get 0 minus -1. That's +1 there. We then get 1 minus 1, so that's 0. And then finally here, 1 minus 3 gives us -2. That's the vector AC there. And then finally here, we have the vector AD. So for the vector AD here, this is D minus A. So what do we get in this case here? We get -2 minus -1. So just be careful with the signs here. This is -1. We then get 3 minus 1, so that's 2. And then finally here, 4 minus 3 gives us 1. Okay, so we've got the 3 vectors that we need here then. So in that case, to find the volume here of a tetrahedron, don't forget the following result then. So V is equal to 1/6 of the scalar triple product. Okay, so in this case here, it will be the vector AD, dotted with the following cross product. So it's the vector AB cross with the vector AC. Like so. Okay. So this part here, right, this is just the scalar triple product. And as we mentioned for the previous question, we can easily evaluate this by finding the result of the 3x3 determinant, right? Just evaluating that 3x3 determinant. So what we get here then is 1/6 times by the following 3x3 determinant. I get 1 3, 1. 1, 0, minus 2. And then finally we get minus 1, 2, 1. Minus 1, 2, 1 there, like so. So all we need to do here now is evaluate this 3 by 3 determinant. Again, just like we saw for the previous question, if your calculator can do this, that's great. You can just evaluate it using your calculator. If not, you just have to do it by hand. But again, it's nothing too challenging here. So what do we get here in this case then? We get 1 over 6 times by, so this in square brackets here. I'm going to get 1 times by the remaining 2 by 2 determinant. So 1 times by, so I get 0, minus 2, 2, and 1. Like so. We then get minus 3. Don't forget this just alternates, right? So it's plus, minus, so on and so on. But we are only just expanding along the top row anyway. I get minus 3 times by the remaining 2 by 2 determinants. So across this row, this column, we get 1, minus 2, minus 1, and 1. Minus 1 and 1 there. And then finally here, we get one lot of the remaining 2 by 2 determinants. So plus 1 times by this remaining 2 by 2 determinant here. You get 1, 0, minus 1, and 2 left over. Like so. Obviously, you don't have to write the 1s here as these coefficients. I'm just doing it just to show you how I've expanded here. So in that case then, let's evaluate the square bracket here. So get 1 over 6 on the outside. So inside the square bracket here, what I get then is 1 times by this 2 by 2 determinant here. So this is 0 times by 1, which is 0, minus 2 times by 2. So that's going to be 4 there. Okay, so I get 4. This 2 by 2 determinant here is 1 times by 1, so that's 1. We then minus 2 times minus 1. So what I get here then is minus 1, but because we times it by minus 3 times by minus 1 gives us positive 3 there. So plus 3. And then finally we have this 2 by 2 determinant here. So 1 times by 2 is 2, minus 0. Times that by 1, we get plus 2 there. Okay. So what I've got here then is 1 over 6 times by 4 plus 3 plus 2. So this bracket here evaluates to 9. Get 1 over 6 times by 9, which gives us 9 over 6, which is just the same then as 3 over 2. Okay. And there we have it. So this here then, this 3 over 2, this is the volume of the tetrahedron. So let's just write that down as well. So volume is equal to 3 over 2 there. Okay. And there we have it. So that gives us the solution there to the very last question, question 2. And that brings the end then of this video here on the scalar triple product.